Okay, these are the notes over simple harmonic motion. First, this describes any motion that represents periodic motion describes any motion that repeats over and over and over again in the same way. So some examples are orbits, uniform circular motion, and simple harmonic motions. These are all periodic. So question, would a bouncing basketball be periodic? And the answer is no. Actually, the answer could be yes, depending on the way you look at it, it's bouncing over and over. But the reason it's no is because it's not doing the same thing over and over. So if you drop the basketball from this height, it's going to fall, and then it's going to bounce back up, but then it's only going to bounce back up to this height. And then it's going to fall, and then it's going to bounce back up, but now it's only going to bounce back up to this height. And so over time, even though it's doing relatively the same thing over and over again, it's not consistent, and so therefore it's not periodic motion. For it to be periodic motion, it has to be repetitive, and it has to be constant. So if periodic motion takes place in one dimension along a straight line or a curve, this is known as an oscillation. And so what I mean by a straight line is if you have, say, a spring hanging from the ceiling and you've got a mass attached to it, and you pull it down, it's just going to oscillate back and forth along that line. Or if you have a pendulum and you pull it back, it's now going to oscillate back and forth along that curve. All right. Simple harmonic is a special type of periodic motion. It's kind of like a rectangle and a square situation. Periodic motion, simple harmonic is periodic motion, but periodic motion is not necessarily simple harmonic. For an object to show simple harmonic motion, it must follow three things to be true. If you can show one is true, then they are all true. If one is false, they are all false. So the first thing you have to show is that the net force on the object is directly proportional to the object's displacement. So for example, if we look at a spring, the force on a spring is equal to kx. And so x is the distance from the origin, and as long as you are, it means that it's got to be linear, because if you increase x, you got to increase the force directly. Number two, the object's motion can be modeled as either a sine or a cosine function. So basically, you are moving up and down like that. And we'll get to what that means a little bit more later. And then finally, the period is independent of the amplitude. So in order for it to be simple harmonic motion, like for a pendulum, it doesn't matter how far you pull it back. For a spring, it doesn't matter how far you pull it down. You know, within reason. You don't want to break the spring and you don't want to break the string, obviously, but it doesn't matter if you pull it down a centimeter or 2 centimeters, it should still be simple harmonic motion. So how can we disqualify the basketball as simple harmonic motion using these three criteria? Well, first of all, the force of gravity is not, the force of gravity is technically directly related to the height. The force of gravity is not related to the height. So force of gravity equals mg. There's no height qualification there. So as the ball falls, the force of gravity doesn't change. So there's no change in the force of gravity. Notice the spring's force will change throughout. As it gets closer to the origin, it's going to get smaller. As it gets farther away, it's going to get larger. So that's one way. Second way, it can't be modeled as a sine or a cosine. So sine or cosine have to be consistent, right? But if you do the basketball here, it would look more like this. You'd have a peak, and then you would have a smaller peak, and then you'd have a smaller peak, and a smaller peak, and a smaller peak, until you got nothing. And so that's really not a sine or a cosine wave, not exactly anyway. And so that's one way to disqualify it. And then finally, the period is independent of the amplitude. Well, the higher you drop the ball from, the longer it's going to take to fall. And so since it's not changing, since it is changing the period, because if you lift it up, it's going to take longer to fall. That changes the period, disqualifies it on count 3. Okay, so these are the most basic formulas you will see with springs and pendulums. So for a spring, the period is equal to 2 pi square root of m over k, where m is mass and k is the spring constant. And for the pendulum, it's square root of 2 pi L over g, where L is the length and g is the acceleration due to gravity. So these are the only factors that affect the period of the spring and the pendulum. There's 2 factors. For the spring, it's mass and the spring constant. So if you have more mass, since it's in the top, more mass is going to give you a longer period. And if you have a higher spring constant, that's going to give you a shorter period in the bottom, in the denominator. For pendulums, the length is important. The longer the string is, the longer your period. And the acceleration due to gravity is important. So if you have a weaker gravity field, you're going to have a longer period as well. Okay, then we've got frequency is 1 over the period, and period is 1 over the frequency. We did that when we did circular motion. So real quick, I'm just going to talk about something called omega. I'm going to just briefly bring that over here. It's the Greek letter. It looks like a W. Like technically it's supposed to look like this, but you know, I can't draw that well. So it's going to be the Greek letter omega. Omega is the angular frequency, and it's called the angular frequency because it's basically how fast it makes like how fast it's covering an angle. So it's essentially how fast a radian you get per second. So whereas the frequency, you can define it as the number of oscillations divided by the number of seconds, the omega would be the number of radians that you're covering per second. And so it's going to be a little bit different than the frequency. It's basically 2 pi divided by, I'm so sorry, I did that wrong. It's going to be the frequency divided by 2 pi is equal to omega. And the reason you do that is because the frequency is 1 full rotation, and the angular frequency is just 1 radian. And it's a little bit difficult to think about because usually we deal with pi's in circles, but remember if you're dealing with a sine wave, 2 pi would be from there to there, okay? So we got everything defined now. Let's go on to the next slide. Basically, so let's talk about graphs. So simple harmonic motion graphs are the same as linear motion graphs in the sense that velocity is the slope of the position versus time, and acceleration is the slope of the velocity versus time. The graphs of all of those are all sinusoidal. So what that means is they all look like sine curves. All simple harmonic motion graphs should be smooth curves. Okay? So to begin with, the position on a simple harmonic motion graph is given by the equation x equals a cosine 2 pi f over t. And sometimes remember that omega was equal to 2 pi was equal to f divided by 2 pi was equal to f divided by 2 pi. Then you could plug that in and you would get x is equal to a cosine omega t as well. So if you're looking for just the angular frequency, know that that could be the way you look for that as well. Also look if you read through, whenever number is outside, cosine is going to be the amplitude. So whatever number is right here is going to be your amplitude, and whatever is inside with the t is going to be equal to 2 pi f. I wrote this wrong. I forgot to put the division sign there. Notice that makes the inside omega t, which is equal to theta. So if you take a look at, basically, if you'll take a look at that GIF that I inserted into the thing, you can see how this moves as you move around it. The radius is essentially what your amplitude is, and you could figure out how to find the x component or the y component. It should be the same. So basically, if you want to find where you are at any given point in time, you would just need the formula a cosine 2 pi ft, and if you could define those terms a and f, you should be able to find where x is. That's how you would go about this. Now, so let's look at this part. We're going to look at how a block, basically a block hanging from a spring, we're going to pull it down, set it into simple harmonic motion. What does the graph look like? Okay, so First of all, we're pulling the block down a small distance to begin with, which means that x is going to start down here. Okay? Now, I know it's going to start down there because it's starting at its farthest point from the 0 mark. So basically, this is 0, this is our max negative, and this is our max positive. All right? So here's the period. So I know that at that time, I need to be back where I started from. Okay? So the reason I know that is because the period is the time it takes to make a complete oscillation. So I'm going to get back to where I started. And then therefore, in the middle at t divided by 2, I've got to be at the max point. And so I can fill the rest of this in. And remember that it should be a smooth graph. So forgive me if this does not look smooth, but it should look something like that. Now, the slope of your graph is what the velocity is. So right here is on the edge of a curve. So if we went backwards, it would look like this. So the slope of my velocity at that point is 0. And where my slope is the greatest is right here, right there. So I know that I've got to have a positive, and notice it's in a positive direction. So I'm going to have my positive slope at the greatest point there. And then at the top, I'm back to having a slope of 0. And then at t, right here at t equals, I guess, or t equals 3/4 of the period, you have a negative slope again. And then we're back to 0 right here. And that's just going to continue to repeat. And so your velocity graph would look like this. Now, if you're in calculus, you should notice that those are the derivatives of each other. Okay? Now, an acceleration graph is the slope of the velocity graph. So right here, you'll notice we have our maximum slope. So right here is our maximum slope. Slope is 0, maximum negative slope. Slope is 0, maximum positive slope. So what I'm going to do is I'm going to graph that. My maximum positive acceleration is going to occur at 0. At the 1/4 point, I'm at an acceleration of 0, and then maximum negative acceleration of 0, and then back to the top at the period. And then that's just going to repeat again. And again, this should make some level of sense. Where is the, if I'm looking at force for a spring is equal to kx. So where is the force the greatest? The force is going to be the greatest at x. And this is where that negative comes in. Force is equal to negative kx, because if it's equal to negative kx, that means when you pull it down, whenever the x is negative, it's going to be pulling in the positive direction. And then when x is 0, there is no force. When there's no force, notice there's no acceleration. All right? And so then we could keep going, but now I need to draw my acceleration. I'm so sorry. Let's see. The sound effects truly do help. Okay. And then the force is going to mock the acceleration. Even if you didn't know this, F is equal to ma. And so the force should go in line with the acceleration. So we have the force following the same pattern as our acceleration. All right, that leaves us with momentum and our energies. All right, so this gets a little tricky. So momentum is mass times velocity. Well, the mass is staying the same, so our momentum graph should mimic our velocity graph. So here's our velocity graph. All I got to do is multiply it by m. All right, that's going to mean that it's going to follow the same path because m is a constant. So basically, if I multiply this graph by, say, 3, then it's still going to go up and down in the same pattern. And pretend these are smooth. I apologize. Kinetic energy. Okay, so kinetic energy, if you'll remember, is equal to 1/2 mv squared. All right, so notice that if I do 1/2 mv squared, I can't go below because v is squared. So even though the velocity is negative over here, right there, I can't hit 0 because it's squared. So if you square a negative, it's a positive. So rather than going up and down below the 0 mark, instead, the velocity starts off at 0, so the kinetic energy will be 0 there, and it will be 0 whenever it gets back to 0. So each point where my velocity is at 0, I'm going to have a 0 for kinetic energy. But wherever my velocity is at, either the crest or the trough, I'm going to have a max point for kinetic energy because it can't go below 0 because it is squared. So it's going to look something like this. Okay? Now, to finish this up, we've got potential energy. So the potential energy of a spring, if you'll remember, is 1/2 kx squared, which means that I'm going to have to look back at this one. And again, just like with velocity, since the x is squared, we can't have anything in this negative section. So there's no negative section. So what I need to do is identify where x is at 0. That's where my potential energy is going to be at 0. So 0, 0, 0, 0. And then where my x is at its max points, there, 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 and there, my potential energy is going to be at its max points. Now, you should notice, hopefully, that the potential energy and the kinetic energy are opposite of each other, which should make sense. As it gains potential energy, it loses kinetic energy. And as it gains kinetic energy, it loses potential energy, which means the total energy of the system should just stay constant across. Because remember, energy is conserved. All right? So let's ask a couple questions. Where is the velocity at its max point? The velocity is at its max point when x is equal to 0. Notice this right here. So your velocity is at its max point when x is equal to 0. And let's see if that makes sense. As it's coming in, it's being accelerated, accelerated, accelerated. When it gets to that midpoint, so like let's put 3, 0, negative 3. As it's moving from negative 3 to 0, you've got force equal to kx, and it's accelerating that whole way up. Once it hits 0, it stops accelerating. So it's speeding up to that point, stops accelerating at that point, and now it's flipped and the force is going this way. So it's going to start decelerating at that point. All right? That's the reason the velocity is the maximum whenever it's at its end. And if you think about a pendulum, it's similar. Whenever the pendulum is at the bottom is when the velocity is going to be at its maximum. So whenever the pendulum is at the rest point, that's when the velocity is going to be at its max. Okay? All right. Well, I hope that was helpful. And go Deer.